to explore the world outside of our solar system is Dr. Giovanna Tinetti, a lecturer at the University College in London. Please welcome Giovanna.
Thank you. So first of all, I would like to thank the organizing committee of this wonderful symposium for inviting me here today. It's a great pleasure and a great honor. So, as it was pointed out today already, we lost our opportunity to be at the center of the universe back in 1543 with Copernicus. Copernicus was a very bright guy and also very wise because actually he published his De Revolutionibus just before his death, which was a very wise decision because you see, in those years, walking next to a solar planet was really not something user-friendly. Giordano Bruno, in 16, by saying that the Earth is one of the infinite inhabited worlds in the universe, actually was burnt alive because of this statement. So Galileo, when he publishes his dialogue, he definitely takes the support of Copernicus, and it was very important for Galileo. We have already heard today the idea that the Earth was not the center of the universe. So I guess things went even worse in the future, because in 1929, the observation of the relative motion among galaxies done by Hubble was interpreted as an evidence of the cosmological principle. And I'm sure you will hear much more in the talk of Paolo De Bernardis after me. And so this idea that there is really no position or galaxy in the universe that is privileged. And even more later on, with the discovery of the electromagnetic fossil radiation at 3 Kelvin, really provided the experiment and showing that there is a unique thermodynamic origin between the universe and the present stellar era. So, focusing on our own galaxy, Galileo observed the Milky Way and, quite astonishingly, published that it was a multitude of stars, which, of course, was extremely bright thought for that time. The first planet orbiting a star different from our own sun was detected in 1995 by the equipe of Mayor and Queloz from the Observatory of Geneva. And this first solar planet, 51 Keck B, was actually a gas giant planet orbiting extremely close to this parent star. You can see, based on this graph, 51 Keck compared to the distance between the Sun and Mercury. And certainly was not predicted, theoretically, that an object like this could exist, because, theoretically speaking, the community was expecting that this sort of planet should form more in the outside part of the solar system in order to accrete enough gas and dust and material. So the discovery of this planet was extremely important, also because all this theory of planetary formation needed to be revised and understand better how planets form and the mechanism of migration. Certainly this 51 Keck B was not an habitable planet. We already said that it's a gas giant, and on top of that, orbiting so close to the parent star, we can say it's a part of this class of objects so-called hot Jupiters or rosters. So gas giant planet like our own Jupiter with temperature that can easily reach the 1,000 or 2,000 Kelvin. And some of those, we think they might be tightly locked since they're actually orbiting so close to the parent star. So after the first discovery, the count for exosolar planet has gone up to 405 planets. And the kind of technique that we used are being used to discover this planet, we are already seeing 51 Keck B, which was discovered with Doppler or radio velocity technique, both radial velocity technique and astrometry share basically the idea that what you try to measure is the wobble of the star. The star and the planet actually are both orbiting around their center of mass. And so if the planet actually is massive enough, also the stars start to wobble. And so you can definitely measure that wobble with Doppler effect or with astrometry. And so in that way, you can infer some of the property of the planet, in particular the mass. Another very successful technique has been used to discover planet, the transit one. And in this case, basically, we are looking at the transit of the planet in front of the star. So it really depends how is the inclination of the orbit with respect to the observer. And the entire idea is that you have the flux of the star that is decreasing because of the passage of the planet. And so in this case, we have the so-called primary transit. And when the planet is actually masked by the star, then we have the so-called secondary transit. I will go back later talking about this particular two technique. And this technique was, the primary transit was pioneered by the team of Charbonneau in 2000, and the secondary transit by the team of Deming and Charbonneau in 2005 with Spitzer. Another very successful technique, more recent, I would say, is the microlensing one. In this case, basically, you're using a gravitational lens as a magnification. So a star that is actually acting as a lens, so you can basically detect a star very far away. And if the star has a planet, you should see some cuspids, some spikes, giving you basically the property of the star and the planet. And the indirect detection, of course, so the idea is you can somehow mask the contribution of the star and really focus on the presence on the planet. And I'm just giving you some order of magnitude of the difficulty of this technique in the case of a Hertz-sized planet, so a pretty small object. For 1 photons coming from the planet, you need 10 power 9 to get rid of 10 power 9 photons in the visible coming from the star. And this number goes down to 10 power 6 photons in the infrared. But despite the difficulty, already some very interesting results came out in October 2008 by 3 different groups. And I'm showing you here just the result of one of those, Clamping and collaborator, looking basically at the direct detection of an extrasolar planet using Hubble. Of course, in this case, the planet was very far from the star, just to simplify the type of detection, but it's an extremely interesting result. So where are those planets? Well, it depends what kind of technique you have been using to detect them. In particular, if you're using radial velocity, astrometry, or transit, then very likely you're looking at star very close to our sun, so we're talking about the solar neighborhood. And on the contrary, for microlensing, it's actually easier to detect objects that are located more close to the galactic bulge, because you have actually a higher density of star there. So just to give you a brief idea of the characteristic of the extrasolar planet that we have detected until now, as you can see in this hit parade of discovery, there is a huge variety of situations. In particular, for the moment, the lightest objects, it's about 2 Hertz masses, and we'll discover with the radial velocity technique is this super Hertz called Gliese 581d. So we're getting very close to the Hertz mass size. But although it's extremely interesting to go into the realm of very light object, I would say what's wrong with being fat, in the sense that right now in the extrasolar planet community, we are actually finding a lot of objects that are not precisely the mass of the Earth, but are basically have a mass that goes between more or less 2 and 10 Earth masses, and we call them super Earth. And this object could be easily Neptune-like planet, in the case they're going towards the 10 Hertz masses, or they could be basically some big high C planets or some terrestrial one more similar to the Earth or Venus in our own solar system. And again, these objects are extremely interesting because we don't have anything like that in the solar system, and so the curiosity is pretty high. And I would say, why not thinking that they might be habitable as well? Okay, so our position in the solar system is very favorable because we are located in the so-called habitable zone of the Sun, meaning with that in an area for which water can actually exist in a liquid form. And so actually on our own planet we have the pleasure of have a water cycle, which is extremely important for the life as we know. Just as a reminder, the habitable zone actually will change in the case you change the star, because of course if instead of a G-type of star like our own Sun, for which the habitable zone is located at 1 astronomical unit of distance, you're basically choosing a star like an M-type of star, which is much colder. Then, as you can imagine, in order to keep the temperature to have a water liquid, you actually need to get pretty close to the star. So the habitable zone is actually shrinking down to 0.1 astronomical units. And just the opposite, if you're considering a star which are actually much hotter than our own Sun, you need to be a little bit more far away in order not to be too hot. Okay, I know that Galileo didn't like too much of the idea of having orbits which are eccentric, but I'm sure it was a genius. So I guess seeing the experiment that despite the fact in our own solar system all the 8 planets are roughly circular orbits, in the case of exosolar planets, 60% of the objects discovered are actually are having a non-zero eccentricity, and actually some of them have extremely high eccentricity. And so certainly the property of being eccentric in a case of an exosolar planet, we don't yet know if it's a standard situation, but it's certainly not that rare. And so immediately it's quite interesting to start to think, even if it's just a theoretical point of view, but I would really love to see some experiment there. What can be a season on a planet for which you can start to play with the tilt of the axis and the eccentricity of the orbit. As you can imagine, the overall concept of season is changing, the photochemistry is changing. If you believe in models, then models are basically telling you that if you don't increase your eccentricity at a level too higher than 0.2, then you still be okay. So you have an atmosphere that should actually more or less try to buffer a little bit the extreme of being too far away from the star or too close in. But as soon as you touch eccentricity much higher, then it's probably a little bit harder for a planet to recover and stay in the so-called habitable zone. But again, I guess the observation will tell us a little bit more. Among these 400 planets that we already know exist outside there, 60 of them are actually transiting. And so I briefly mentioned before that a planet that is transiting is basically at a certain point passing in front of its parent star, so between the star and the observer. And because of its presence, the brightness of the star is dimming. And so by measuring basically the flux of the star and how much is decreasing because of the planet, what you do is actually measuring the ratio between the surface of the planet with respect to the surface of the star. And just to give you order of magnitude, we are talking about 1%. In the case that the star is a G-type of star like our own Sun, and the planet is a Jupiter type of is a Jupiter-like planet. But the same number actually is okay for an M-type of star, so a star that is smaller than our own Sun, and a super Earth, so a fat Earth. So as you can see, in theory, if we had, if 1% is something we can reach relatively easily, doing Jupiter transiting G-type of star or super Earth transiting M star should be more or less the same in terms of difficulties. And 1%, I would say, today is probably not, I'm not saying it's straightforward, but it's certainly not impossible, because it was actually done by my 2 students, Ingo Wollman and David Kippen, from the hills of London with an amatorial telescope, 35 centimeters. And they actually could detect for the first time the transit of this planet, HD 80606b, which is extremely eccentric, the most eccentric one up to date. It was predicted to transit by Greg Laughlin, and they could do that. So 1%, I would say, is probably okay. Now, if you, instead of a super Hertz and an M type of star, you really want to have a look at a Hertz-sized planet and a G type of star, then you need something more sophisticated than the hills of London and 35 centimeter. You actually need Kepler, the mission, of course. And so in this case, we're talking about number as small as 0.1%. So you understand immediately why you need a mission in space and something as sophisticated as Kepler. Now, Galileo, of course, did a wonderful job in his Sidereus Nuncius, basically detecting the Jupiter's moon back in 1610. And of course, if we want to push this concept in terms of exosolar planet, what about exosolar moon? So exomoon. In particular, they could be extremely interesting in the case we're considering moons that are orbiting gas giant in the habitable zone out there. And David Kipping, my PhD students, have a look at that, in particular in terms of detection. And what he found out is basically if the moon is actually more or less the size of the Earth, or in any case, an object that is not so small, then what happens basically if you have the Jupiter planet and the moon that is orbiting, like a little bit in the case of the Doppler effect, what is happening is that you have the Jupiter that is wobbling a little bit. And so this wobbling actually could be detected with transit technique. And in particular, it could be detected with Kepler. I mean, it's now at Harvard looking into this. The idea is basically you should combine what we call transit time variation. So basically, if this is the transit depth, and so is due to the decreasing of the flux of the star due to the transit of the planet, then if there is a moon, you should first of all expect some variation in the transit time. But on top of that, you should expect some transit duration variation. Okay? And again, because these two efforts are basically combined, are measuring this wobbling, this change in both position and velocity of the moon. So let's see if we'll have exomoons soon. Now, another reason why transits are so interesting is that apart from exomoon and detecting the radius of these planets, you can actually also infer some of the properties of the planetary atmosphere of these objects. And at today is actually the only technique that is telling us something about these atmospheres. And if you're talking about atmosphere, then we're talking about basically this very thin layer, so this very thin annulus, compared to the radius of the star square, because it's, of course, it's the surface of the star. And so we're talking about a number that, again, is pretty small, 0.1%. It's no more than 1% we have seen before. And so also for this number, we needed some very powerful telescope in space, like Spitzer and Hubble. And definitely Spitzer and Hubble really opened a new era for this type of field. So the idea you want to use if you use a primary transit is that you can repeat your observation at different wavelengths. And so you would expect that if there are molecules absorbing in your planetary atmosphere, the radius that you're actually measuring, which is actually, again, proportional to the transit depth, will change with those wavelengths. And so in particular, this is something we tried back in 2007 with Spitzer, and we proposed that actually even just the 3-band photometry were just, again, free broadband, but we proposed that actually water has such a large signature, an important signature in the infrared, that even 3 broadband was enough actually to detect its presence. Now, of course, back in 2007, with this particular primary transit technique, that's what we could do. And then more measurement came in, also with Hubble, and I would say this spectrum, this new spectrum we have been working on with Mark Twain, Peter Deroux, and Gautam Vasisht at JPL, was recorded with NIGMAS, and I would say is no more 3 broadband, is actually a spectrum. And even if the resolution is still low compared to the spectra that Angioletta can see in the solar system, but still, we can already pretty clearly see the spectroscopy signature of water, methane, CO2, and possibly CO. And like this, we have our planets, and so we can already start some comparative planetology, at least for this class of gas giant planet that have been discovered. Now, Galileo also gave a very nice contribution interpreting the sunspot, and we heard this very interesting talk in the afternoon about this. But star spots are also very important if you want to do transit, because as you can imagine, they're competing with the signature of the planet. In particular, for stars that are very active, you need to be very careful, especially if you are in the visible or near infrared. The presence of a spot, well, in this case, is okay, because basically this is just an example of a planet covering a star spot, and so the signature here is due to the spot. But sometimes it's actually even worse than that. You have to be very careful in not misinterpreting the presence of the spot or the presence of the planet. So definitely star spots are an extremely interesting subject if you want to do transit. I basically talked about a little bit about primary transit technique, but there is a complementary technique, secondary transit, pioneered by Charbonneau and Deming in 2005. And according to this technique, basically, you're measuring, first of all, the star and the planet when they are together, and then you're basically waiting for the planet to be masked by the star. And so you can subtract out the contribution of the star and basically re-record the light that is directly emitted, or if you're in the infrared, or reflected by the planet if you're in the visible. And so, again, just to give you order of magnitude, with secondary transit technique, what you're measuring is, again, a little bit something that goes with the ratio of the surface, because, of course, in this case, the size matter. But also the ratio of the flux of the planet with respect to the flux of the star. And so, again, if you're in the infrared, comparing basically planets that have a temperature of 1000 Kelvin with respect to 300 Kelvin, you can see there is a difference. And so, certainly depending what the temperature you want to probe and what is the contrast ratio, you want to select exactly which wavelength you want to be in. And if you are in the infrared with secondary transit, you can also probe the structure of the thermal structure of the planetary atmosphere. So not only the presence of molecules that are absorbing there. In particular, if you see in some molecule in absorption, then chances are that your temperature is actually decreasing with altitude. And just the opposite, if you see in a molecule which is emitted by the planet because of emission type of spectral signature, it might be because the temperature is actually increasing with altitude. So this is just an example of what we can do today, combining a measurement from Hubble and Spitzer. And this is the planet HD 189733b, one of these gas giants, one of the most studied one, because the star is actually pretty bright. And if you start to put together all the data that were recorded with different instruments on board the Spitzer, like IRS, this beautiful spectrum recorded by Grillmer and collaborator, Nature paper in the autumn, and several other photometry data recorded by Charbonneau, Knudsen, and Deming, and the spectroscopy data recorded by our group with NIGMAS, then you can really start to see what's going on. And again, we have at least a couple of planets at the moment for which we can collect so many data, and I hope that in the future we'll have even more. And we can also infer a lot of the properties of this planetary atmosphere, but just looking at light curves or phases. In this case, you don't need necessarily to have a transiting planet. It is enough to have a planet that is orbiting so close to the star, for which actually the contribution of the planet itself is not negligible compared to the star. And so, again, Galileo was pioneering this idea, looking at the phases of Venus back in 1613. And so we are doing a little bit of that. This is, for instance, an extremely interesting result obtained by Harrington and collaborator in 2006 with Spitzer, looking at sunlight curve of this Andromeda B, which is a planet that actually does not transit. But again, its contribution and the changes of its thermal structure throughout the orbit is actually important enough that can be recorded with Spitzer. And another example, a beautiful light curve recorded this time with Kepler. So in the visible, looking at the planet, gas giant planet at TP7. And in this case, since this is a transiting planet, you can clearly see, first of all, the primary transit when the planet is passing in front of the star, and then the secondary transit when the planet is actually hidden by the star. So where we can put our bet for the future? Well, certainly I think that super-Earth and possibly Earth-sized planet, hopefully in the habitable zone, will actually be quite a dream to have in the next future. This is just a slide giving you a synoptic view of the spectra in the infrared of the terrestrial planet in our own solar system, where actually you can see pretty clearly that in the case of the Earth, there is this extra signature due to ozone that is not present in the case of Mars and Venus. And so we all hope that when we'll have such type of spectra of super-Earth, if not Earth, out there, we might be able to, first of all, understand their atmosphere and maybe even look for biosignature. Certainly what will happen is the James Webb Space Telescope, the new generation of space telescope. And if we look at some calculation and some modeling, we can probably infer that James Webb will be able to do habitable transiting super-Earth, and probably Earth-sized planet, if not really Earth-like. Earth-like might be a little bit tough even for JWST, but certainly transiting hot Earth-sized planet, it will be feasible with such a nice TORI. And another possibility is more in the realm of course, are not there yet, but something that has been thought of and planned, is this mission proposed by Mark Twain and NASA, and we are thinking of proposing this to ESA as well, is a mission completely devoted to do characterization using transit technique of exosolar planet. And so it's the simplest mission concept you can think of for doing exoplanet characterization, combining basically an instrument that is very stable, like Spitzer was, and that was one of the reasons why this telescope was so successful for doing exosolar planet. I'm basically combining this with two spectrographs in the infrared and the medium infrared. But, there are also other possibilities. The legacy between space and ground probably was something to bear in mind in the future. There are very large telescopes or extremely large telescopes that are being built in the next decade. And there are other mission concepts being proposed to NASA or ESA, like a small, medium-sized telescope with coronagraph to do direct detection. Or something even a little bit more challenging, like the New World Observer, this idea of having an occulter, so basically a mask that is actually nulling out the contribution of the star and is actually flying several kilometers away from the telescope, able basically to produce some spectra of some Earth-like planet. So I guess the future for exosolar planet is pretty bright. And on this thought, I would like to conclude saying that if Galileo were alive today, it would probably work on exosolar planets. Thanks for your attention.
There is time for one question for Giovanna. Well, perhaps then let's... Oh, right.
From where we are now, where do we have to go to detect Earths around solar-type stars?
So Earth-like planet around...
One Earth mass planet around the star like the Sun. How far are we from being able to do that? What do we have to accomplish?
Okay, so, well, if you really want a Earth-like planet around a Sun type of star, then probably, well, Kepler will be able to detect objects like that with transit technique. If you want to characterize their atmosphere, probably Earth-like planet for a Sun type of star, it might not be easy even for JWST. It's certainly not the sweet spot. Certainly what transit can do in the future is looking at habitable super-Earth, especially around M-type of star, which is extremely interesting type of exercise. But Earth-like planet around Sun type of star, again, is not the sweet spot. So probably you need to go for direct detection in that case. And so launch one of this mission that is specifically designed for doing that kind of problem.
Thank you, Giovanna.
Thank you.